If you have a deep liquid, H is much greater than lambda. This go to infinity. Hypertangent go to infinity equal to 1. So this become 1 here. So this dispersion relation under the deep liquid assumption, we have this. Okay, the solution form for the dispersion relation. Okay, when H is much greater than lambda. Okay, and for this term here, again, if you assume this term, this parameter is much greater than 1. So this 1 plus this will be equal to, almost equal to this, okay, because this is much
greater than 1. So inside this bracket, okay, can be even simplified, okay. And then how can we have this? Since our sigma, okay, over log G take a square root is 1 of length scale. If we, okay, we have been using this before, okay. Sigma over log G, okay. This is a if you try to check the dimension, this is the dimension for this. This is the length scale dimension. Okay, this is length scale dimension. So when this length scale, okay, when this length scale is much greater than lambda, so that means sigma over log G is much greater than lambda square, because this is, okay, it's a square root of this. When you have this is a compared with the lambda square, right? So this is much greater than lambda square. Okay, for this term here can be even simplified. Okay, 1 plus this will be simplified as only this, right? So we have c squared over log G over GH equal to lambda times 2 pi h times this term here. Okay, and this 2 pi and 2 pi is cancelled, become have 2 pi here because there's 2 pi square, and we have sigma here, right? And log G here, and lambda square divided by 1 lambda become 1 lambda, and we have h here. So this is a dispersion relation when you have this, okay, assumption here. And this assumption we call this capillary wave. Okay, capillary wave. Okay, so capillary wave will be come out with what? We come out with can modify our so-called deep liquid wave. Okay, as you can see here. Okay. Our previous solution is like this. If you compare with previous solution, okay, this is our previous dispersion relation. Okay, this is lambda function. This is c function. We have this without consider any surface tension. When you consider surface tension, okay, become like this. Or dispersion relation change, right? Only change is here. Okay, when we have to consider this, okay, we have the capillary wave. For the capillary wave, the dispersion relation for this will be like this dash line here. Okay, and this is so for the deep liquid wave. This is for the shallow liquid wave, right? So we have the 3 approach. This is shallow liquid wave approach to a constant. Deep liquid wave approach to proportional to a lambda, right? Because this is equal to 1. This is equal to 1 for the deep liquid wave. So this is equal to 1. Become like this, and if you consider the so-called capillary wave is this relationship. It will be written like this. So the solid line here we complete the dispersion relation. Okay, for all case. Okay, so for this part we can use in the capillary wave. Okay, can satisfy by the capillary wave assumption here, and this part can satisfy our shallow wave, deep liquid wave, and this part is a shallow liquid wave. Okay, and since our considered surface tension only modifies here, so the effect of the surface tension only modified only in the deep liquid wave here, deep liquid wave here. Okay, and this is under this condition we can modify this. The rest should be the same. Okay, we only can by only consider surface tension under this condition here. Okay, we have effect on our dispersion relation. Okay, and section 6.5, I think we will neglect it for a moment. Okay, we will start from 6.6. Okay, and 6.6 is just repeat. Okay, since we get C2 already, C1, C2. This is our, okay, Rossi potential, and this is our
kinetic bounding condition, you can get our C2 as previous here, right? We I already tell you like here, okay? By using the kinetic bounding condition, I can get C2, okay? And this is just try to deliver it here, okay? Here, okay? I have a dispersion area and try to find C2, and this is our kinetic bounding condition. By applying this into this kinetic bounding condition, I can find out my C2 constant. Okay, so C2 constant. So I can get my complete velocity potential. When I have a traveling wave, this is a traveling sinusoid wave on the top. And this is the velocity potential look like to govern the flow field underneath. OK， 所以这个是表面上面有一个 sin 波的一个行进波，这是它行进波的形式。当你有这个行进波的时候，我下面流场的 velocity potential 可以写成这样，所以知道 velocity potential 就知道流场。OK， 因为 U 等于 partial v partial x， 对 ，V 等于 partial v partial y。OK，so once we know the velocity potential， OK， for this function， OK， under this traveling wave on top。And this velocity potential, once we know the velocity potential, we can find the velocity field because U is equal to partial v partial x, V is equal to partial v partial y. Okay, so any point, x, y, t, any moment, any point, I know the velocity, okay, for this flow field. And also I have additional so-called dispersion relation. This is a dispersion relation, okay? So this is by using the dynamic bounding condition, our C wave speed, this is C here, and lambda here is not independent, should follow this. Okay? You cannot assume any C and lambda here. Okay? C and lambda should satisfy this dispersion relation. Can you get me? Since you are assumed the epsilon sine 2 pi over lambda x minus ct, C and lambda cannot assume arbitrary. Okay? You have to satisfy this dispersion relation. Okay, in order to satisfy our dynamic boundary condition. Okay, and this dispersion relation can be simplified if you are using the shallow water liquid wave. Okay, under this assumption, we can have this simplified dispersion relation. If you have deep liquid wave, okay, our dispersion relation will become like this. If you have capillary wave, this is capillary wave assumption. We have the dispersion relation become like this. Okay, so that kind of conclude just what we talked about in the previous. Okay, just last previous hour we mentioned everything here. Okay, and next what we try to do, we try to find the complete potential for the traveling wave. Okay, so I have a velocity potential phi, and what's the complete potential definition? Complete potential definition. Or F is the complete potential to be equal to 3 right? So I try to find out this. Okay, because when I know the complete potential, that's much easier later. Okay. So here, this 6.6 here, we try to evaluate what's the complete potential when I have a traveling wave on the top. The same boundary condition, I already have the velocity potential. So next I'll try to find out the stream function, right? So once we have the velocity potential and what's the relation between our velocity potential and the stream function side, U is equal to partial psi partial y, right? And equal to partial v partial x. So I can find out partial v partial I by take this side, take a derivative is x, this is derivative x, and try to integrate with y again, and this is y. So when you have an integrate, I find the constant. This constant not a function of y. So this constant is a function of x only. Okay, can you follow me? You just do the integration for this function. Okay, and this integration will give you this. You can check. Okay, because hypersine become hypercosine, right? This is a y function here, right? And this is a hypercosine become hypersine. Okay. Okay, you can check by yourself. Just try to integrate, and I got an integration constant, fx here. Okay, again, I can using the v is equal to minus partial psi partial x equal to partial v partial y, right? So this is the v velocity. V, velocity in y component is partial v partial y should be equal to partial v partial x minus. So partial v partial x, I take a partial v partial y here. This is a phi function. I already have this. And I can evaluate partial v partial y and take a minus sign and I can have this. So I integrate with respect to x can give me the stream function psi. So this is when you integrate with x, this is integration with x. When you integration with x, you get an integration constant, right? The integration constant is function of y, right? Because you integrate with x, this integration constant cannot be function of x anymore. It only can be function of y only. Okay, when you compare with this, okay, this is from this relationship, I get this, and then from this relationship, I get this. This is the stream function. If you compare this and this, exact the same, right? This is a hypercosine, hypercosine, hypercotangent, hypercotangent, hypersine, hypersine. So exact the same. Only difference is what? This integration constant. Right? So I can assume what? This integration constant should be equal to 0 because this is function of x, this is function of y. Okay, this I can assume this is equal to 0. Okay, because it is a constant, but the constant you can assign any constant. Here we assume this constant equal to 0. Make no difference because the psi with the psi plus a constant make no difference. Okay, psi equal to 1 and psi equal to 2 make no difference. Only the difference delta psi. You remember delta psi give us what? Give us the flow rate between two stream functions, stream line. Okay, psi equal to a constant. Any constant make no difference. Okay. So this is integration constant fx gy here can be assumed equal to 0 for simplify. Okay. So this is a psi function we have. Okay. So we have the velocity potential. We have a stream function. Finally, we can get what? Our complete potential. Right? And what the complete potential, this is the stream velocity potential, this is the stream function we just got. Okay? And then our stream velocity complete potential will be phi plus I psi. This is a phi, okay, phi and plus I psi. Okay, this is I psi here. Okay? I times psi here. But we take a common factor here. Common factor is this C and then hypercotangent. We take this as you can see. Okay, this is a common factor out of this bracket. So everything here should be multiplied with this. Okay, multiply with this. So here we have the multiply with the 2 pi h over lambda, 2 pi h over lambda here, right? So 2 pi h over lambda times this term here. Okay, plus hypercotangent is what? Hypercotangent is okay, hypercotangent will be right? This. Okay. So when you have this, when you multiply this, since you take out from here, so you the hypercotangent, this hypercotangent become hypercosine here, hypercosine here. Okay, you can check. Okay, just I don't think I need to go to the. Okay, so this when you using this solution, you get the complete potential look like this. Okay, and we can even simplify this later. Okay, and how to simplify? As you can see here, this is our complete potential we just written. Okay, we just written this is just copy this to here. This is complete potential. Okay. Okay, and then so as you can see here, we have a hypercosine here. So we for this term here, okay, for this red line and red line, this term and this term, we can combine together. So this we take out hypercosine function. This and inside here we have a hypercosine function. Okay, hypercosine. I'm sorry. Here this is here, right? Times this hypercosine function, okay, and then minus I, and sine for this term here, and I have what? I have this hypersine function here. So all the red line here is composed by these two terms. Okay， 你把这两项合起来就变这一项。OK， OK， 只有做一些移项而已，你看得清楚一点。So on the green line here, these two terms with this can be combined with this. Okay, just kind of rearrange our equation. Okay, and what I use is here. Okay, as you can see, cosine I alpha is equal to hypercosine alpha. Sine I alpha equal to I hypercosine alpha. Later we're using this relationship. Okay, so I have this. Okay, I rearrange the equation like here. Okay, and I copy here. This is I just copy the equation here, and for you to much easier to follow. Okay, this equation and this equation should be exact the same. Okay, should be exact the same. And what I did is what? What I did, I apply. Okay, apply the relationship I just described. Okay, so here is a cosine I alpha. This is alpha. Like cosine I alpha equal to hyper cosine alpha. Remember this. Okay, so here the second term here, cosine I alpha. This is I. This is alpha. Become hyper cosine. Hyper cosine. Let me check. Yes or no? Let me. Okay, here is this is term here and this is term here. Okay, there's a slightly different. Okay, anyway, I can actually. So here we can change it to. Okay. Let me see. This is this term here, right? And this term is a copy here. Okay. And this term, as you can see, cosine minus sine is what? Remember, we have a cosine alpha, cosine beta minus sine alpha, sine beta equals cosine alpha plus beta. Okay, so this is relationship can be applied to here. Cosine minus sine is here, right? Cosine minus sine. So alpha beta can be written as cosine alpha plus beta. So here. For this term here, we can written as cosine alpha, okay, plus beta, okay, plus beta. So later you can this is x, okay, 2 pi over lambda. So x plus y give you z, right? Z is x equal to x. Z is equal to x plus I y here, and the ct minus dt here. So I can kind of superimpose together like this. Okay, so I apply this relationship, cosine minus sine give you this, give me this term here. So the red line, these two terms can be simplified by this term here. Okay. And then here we have what? We have the I, right? This is OI here. So here we have a cosine, sine, cosine. Okay, so what you apply? This term, right? Sine, sine. Okay, so here we have the I, so take out the minus I, so ABC is cosine, sine plus sine, cosine. So sine, cosine plus cosine, sine, right? Give you the sine plus I. So this is this term here. Okay. So we have this term. This is this term, and this can be simplified by this, and plus this term here, and this term have to multiply minus I here. This is minus I here. So minus I times this term, and this is a cosine, sine, cosine. Can be using this relationship, giving the sine alpha plus beta. It give me this. Okay. And then so here again, so we have a cosine function here, and this is a hypercosine and the cosine function here, and we have hyper sine function and sine here. Okay, and so what we try to do is try to change by using this. As you can see, hypercosine function alpha should be equal to cosine I alpha. So this can be changed to cosine I of this. Okay, I times this. And then this hypersine is here, can be changed to sine, and you have to multiply by I. This multiply by I become minus 1. So this is minus I sine I alpha. So this can be changed to sine function. So we have the cosine, okay, cosine, minus sine, right? Remember that. And this minus, because our minus, this minus sign here, become plus sign here. So we can have this. Okay. So here is a more detail. Okay. I just copy this here. Okay. Hypercosine function become cosine function by apply this. Okay. Hypercosine function of this equal to cosine I alpha. This is alpha. So the I times alpha. Okay. And then multiply this. This is and this is minus I. We can apply this, right? This is a hypersine function. I times hypersine function is this, right? So this I times hypersine alpha. So this is alpha equal to sine I alpha. So this is minus all this term here, including this I here, is a sine I alpha. Okay, that's it. Okay, so you can double check. Okay. And finally, as you can see, again, we have a cosine, sine. So we can also using this cosine, sine, and with a minus sign here, give me the cosine alpha plus beta. So this is a final simplified form for our complete potential for this traveling wave. Okay, so there will become Fz of t is function of z and t, right? This is a complete potential. So it's equal to this multiplied cosine function 2 pi over lambda z minus ct plus ih. So this is final form for our complete potential for traveling wave. Okay. Okay. So once you know the complete potential, okay, that later will be you are using the complete potential instead of using the velocity potential later. Okay. This is much more information for this. Okay. What else? Next, okay, what we would like to apply the complete potential, okay, to any particle, okay, on the free surface for the particle path for the traveling wave, okay. Inside this wave here, okay, inside this wave, under this wave, if I have a flow particle, what this flow particle, how this flow particle move, that means we try to find our path line. You remember what's a path line? Path line is follow a flow particle, right? As they move, right? And we'll try to map out what's the path line for this flow field. Okay. So how do you find our path line for this flow field? We have the complete potential like this. This is our complete potential. Okay. If I have any particle, okay, location is x1 minus y1. This is x1 minus this p point, and this I using the minus sign here because this is usually for this point is represented z1, and I take a complete conjugate. So this is a complete conjugate. Complete conjugate is z1 bar. z1 bar give me the x1 minus y1. Since I change the sign here. And so this is the flow particle. Okay, this is a flow particle location of the path line. And I try to find out the dz1 bar dt. That's what? That's a path line. So dz1 bar dt will give you the dx1 dt minus I dy dt, and dx1 dt give you the u velocity, dy1 dt give you the v velocity, and this is minus sign become u minus iv. U minus iv is what? Is our compressed velocity. Remember, right? Compressed velocity. Okay, w, and w is what? W is df dz. If you want to find if you have a complete potential, try to find our complete velocity. Just take a first derivative with respect to z. That's our complete velocity. Okay, that's in our chapter 4. Okay, 第4章有教这个，对不对？你怎么样从 complete potential 求 complete velocity? Okay, and complete velocity definition is u minus iv. Okay, remember. Okay, so once we have the df, right? df dz, and f is here. So df dz, you can take a derivative for this. Can you find out this? Okay, so dz1 bar dt, that's our what? That's our path line equation should be equal to this. Right, z1 is our path line equation. Any problem here? 这地方我们就是要求它的 path line. Okay, we'd like to try to find out the path line for the. Okay, so z1 is our particle path. Okay, so we have this relationship. Okay, we take a df dt. F is here. df dt become like this. Try to check for me. Sine, cosine function z is here. Cosine becomes sine, right? That's This look like correct, right? Okay. And the rest is just a constant. Okay. If, since you have z and you have to multiply 2 pi lambda here, so you have a 2 pi lambda here. Okay. 2 pi over lambda here. So it should be it. Okay. Once you have this relationship, try to do what? Integration with time. Time is here. Right, is a sine function become cosine function, and you have the integration constant c, and c will be cancelled by this. Okay, like here. Okay, and so this is our z1 bar. So z1 bar is what? Is our Ch6 equation. 哎，我们的所谓的那个叫什么基线？那不是基线，中文我忘记了。Ch6 是什么线 ？Okay, this is Ch6 equation. And remember, this is x minus iy. Okay, this is x1 minus iy. So here we can evaluate this, right? You can evaluate this. And when you can compare with z1 with our string function, with our velocity potential, what's the difference here? Okay. Our x1 is this. Okay. X1 is this real part of this, right? And real part of this is what? Will be equal to our phi divided by c, because when you consider this, okay, we have the phi divided by c. It's not so obvious, right? But anyway, we can using this z1 bar compare with our complete potential. As you can see here, compare this term and this term. Only difference is what? Only difference is c here. Can you see that? Here and here, can try to compare. This is cosine function, this is cosine function, the same. And this is hypersine function, the same. Only this here different, right? Epsilon here. We have a c epsilon here. Okay? And only there's a minus sign here, but we don't have any minus sign. So our z1 bar can be written as f divided by c, take a minus sign. Can we do that? Yes, right? Okay? So, and this is equal to what? This is equal to psi plus I phi, right? So we have this relationship, right? So we have easy, okay? z1 bar is our Ch6 equation equal to our f complete potential divided by c, x minus sign. And z1 bar is x minus iy, is x1 y1, right? And f is equal to phi plus I psi, right? So our x1 should be equal to real part of this. And our y1 should be equal to, take a minus sign here, right? And this should be a minus sign. Is that right? Minus sign. Okay? And let's psi here. Okay, so partial psi over c. And then y1 should be psi over c. So what's wrong here? Minus sign here. Take minus sign here. So okay, so we have this y1 is this. x1 and y1. Okay, so our x1 will be minus phi over c. Our y1 should be psi over c. Okay, velocity potential divided by c is our Ch6 x1 coordinate. Okay, string function divided by c is our y coordinate. Okay, for our Ch6. Okay, so x1, since our string function, our velocity potential in the string function is already, already have that before we have this complete potential. So we can divide by c and take a minus sign, give you x1. This is x1. This is our string function divided by c. This c is cancelled. So this is our Ch6 y location. Okay, so give me any. Okay, this is x1 and y1 is on the Ch6 on the. Okay. Because dx1 dt equal to u, that's a Ch6 definition, right? Okay. Okay, so this is a fluid particle, okay, will be follow x1 and y1 location, moving according to the different time and different x and y location. Okay. And what we try to do is what? We try to do is, you can see, we have a